recording. And we're sharing our screen. Okay, and remember, all of the online people, I won't necessarily be able to see hand raises and chat and stuff like that. So if you have a question, just unmute and scream, and we'll figure it out. Yeah, so that's the scoop with that. Then I have a group of people in front of me, and we can see stuff on both TVs, right? And if any of you can't see the TVs very well, you can log into the Zoom from your desk. Just make sure you turn your speakers off so I don't hear myself echoing through the room. But to be honest, sometimes it's the easier way to see what's on my screen is to be on your computer on Zoom. So kind of pick your poison, just keep your mic muted and your speakers turned off so that I'm not echoing. Okay, so you saw this morning, well, hopefully most of you saw this morning, I posted on Slack a link to a up-to-date Raspbian ISO for VirtualBox, and then also a link to VirtualBox. There's also the video that is on the slides that's linked on Blackboard. So, you know, sometime within the next, call it week or week and a half, something like that, is when we're going to start using that. I'll probably be doing it with examples in class leading up to that, but you won't need it until then. But between now and let's call it, you know, end of next week, get VirtualBox installed in your computer and get Raspbian installed. I mean, the process, and I say it in here, is you install VirtualBox, which is a software application. Okay, it's something called a hypervisor, but don't worry about that. It's just, think of it like Microsoft Word. All right, you install it, and then you also download this image for Raspbian. When you launch VirtualBox, it's going to ask you if you want to create a new virtual machine. You say yes, create the virtual machine, and then you'll choose the ISO for installing the operating system on that virtual machine. And then when you hit start, it should go through and launch it just as if you were launching it on your actual computer. Just do the default install. You don't need to dedicate very many system resources. When you're using a virtual machine, it is going to be sharing your system resources on your computer with the virtual machine. So if you're running Windows and Raspbian at the same exact time, and your computer has 8 gigabytes of memory in it, some of that memory is going to be taken away from Windows and dedicated for Raspbian. All right, so you are sharing your system resources. Raspbian is not a very big operating system, so you could give it as little as 1 gigabyte of memory and probably get by. 2 gigabytes might be safe, no more than 4, depending how much RAM you have on your computer. And you don't need to give it very much hard drive space. We're not going to be installing, you know, huge things on there or anything. You're going to be saving like tiny Python files. So, you know, give it your bare minimum resources. It probably is going to give a suggestion for what resource it suggests for Linux. You could even just accept that and move on. But try to get a beat on what your current setup in your laptop is. Most of you probably, if you have a relatively newer computer, whether it's a laptop or desktop at home, you probably have at least 8 gigabytes of memory. Some of you might have more than 8 gigabytes of memory. If you have 16, you know, you can easily give 4 and it won't be a big deal. If you have an older laptop that only has 4 gigs of memory, you probably want to just do the 1 gig shared with it and kind of limp through. I know a couple of students are dual booting, so they're running Raspbian on their computer alongside Windows where they have to restart their computer and launch as Raspbian. That's some extra work. I wouldn't recommend going that route. You know, like in here, I just swiped and I'm on Raspbian. So I think that is the path of least resistance for doing this stuff, but my machine has quite a bit of resources associated with it, so I can create multiple instances. But that's kind of the idea, is VirtualBox is a hypervisor that hosts, it pretends to be another computer running on your computer. And then you install Raspbian on that fake computer, that software-based computer. All right, makes some sense? All right, so I linked some stuff on Slack. Post questions on there. I'll answer them if I can quickly, but realistically, your best source is going to be all the other students who are doing the exact same thing as you, who say, oh yeah, you get that error message, just hit this checkbox and it fixes it. Something like that. So between the whole group, everybody will get that on their machine. I also have had some students ask if they can use other versions of Linux like Ubuntu and things like that. That's fine. I don't care. I just want you using an operating system that takes you out of your comfort zone. But I will be using this Thonny Python IDE thing that's built into Raspbian, just so everybody has the identical experience. So if you're choosing to use a different version of Linux and it doesn't have this installed, either go and find it and install it, or run Python however you want. You'll just be on your own. I'm not going to support 90 different installs of Python, but Thonny isn't anything special. It's just a text editor that happens to have a play button to run your Python program. And this isn't, you know, a major amazing application or anything. It just happens to come packaged with Raspbian. Okay, so I think this was kind of the slide we were on at the very end of class last time. Does that look about right? So, you know, I kind of made this argument that computer programming is hard. Why is it hard? It's because human beings are so good at solving problems that we have trouble articulating how we solve them. You know, so that's a kind of a feather in our own cap, but also is what makes it difficult to go and learn something like computer programming, because we have to dumb ourselves down to the level of this computer. You know, we tend to come in and we have this idea that, oh, computers are so smart, they're so difficult. This thing is an idiot. It can't do anything. We're going to be talking about the nature of the CPU today. And you realize that you really have to dumb things down for a computer and give it the individual little steps in order for it to do your bidding. Okay, when you write code, you're giving this guy individual instructions. Do this, 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 and then this. And if you skip one of those steps, or you're not completely unambiguous in one of those steps, the computer's just going to do whatever you told it to do and do the wrong thing potentially. All right, so we're going to have to retrain our mind to slow down and better articulate problems. And I think I mentioned last time, but I'll mention it again now. You know, what's interesting about that is I think a lot of folks who go into computer science, you know, maybe they go into it because, oh, I want to write video games, something like that. You know, the idea is that as a, we might have these ideas in our head that like, oh, pick your favorite video game. That must have been so complex to write, and that, you know, it's really difficult to do that type of thing. Well, I mean, we talked last time about just walking to class and, you know, you're not even worth your full attention. You're texting on your phone and stuff like that. That's significantly harder than the most complex video game you can think of. We're very limited on the kinds of applications we can write on our computers because we have to be able to fully articulate the solution. We have to be able to tell this thing each and every little step. And we already decided we probably can't accomplish that no matter how hard we try with walking, right? We're not thinking about firing every muscle and things like that. It just sort of kind of happens. So kind of, you know, reframe the types of problems you can solve with computer programming in terms of the types of problems you can fully articulate the solution to. And then where that kind of becomes interesting, and you know, if you guys looked at some of the concentrations we have in the program, you know, probably the top two concentrations are software engineering and AI and robotics, maybe followed closely by cybersecurity. But you know, this whole idea of machine learning. How many of you have heard of machine learning before? Okay, what do you think machine learning is? What would you say? Okay, that's a made-up word, a made-up phrase. So tell me about predictive analytics. Okay, so maybe a decision engine. Anybody have a different definition you want to throw at it? So machine learning is if we're going to just say it for what it really is, it's trying to get this computer to think like us. Well, not think, to act like us, to make decisions as if it was us, right? So you think about like the self-driving cars from Tesla and things like that, you know, they kind of have a starting point. We'll talk about that just briefly here in a second, but you know, then after you've had you know, hundreds of thousands of drivers driving hundreds of thousands of miles, it kind of gets better and better at staying between the lanes, identifying stop signs, you know, things like that. And it got that through practice. Very similar to, you know, how we learn things, right? You know, you start off, you're falling over, you can't walk, can't crawl, whatever. Then, you know, you're trying to put the square peg in the round hole. And finally, you kind of learn from your own mistakes to how to do things, right? Well, a machine learning typically operates around this thing called the neural network. And all a neural network is a computer program that attempts to mimic the human brain so far as we understand it, so far as we can articulate it. So this goes right back to, you know, what I just said a few minutes ago, is that we need to be, anything we tell a computer to do, we need to be able to explain. So we've decided this is our simplified model of a human brain. That's this neural network. And we can build big or small neural networks. There's all these variables to it. That's where cover those in the artificial intelligence classes and things like that. But ultimately the idea, and I'll just give you my, you know, an example of kind of my first experience with a neural network years and years and years ago. It's that we built this little neural network piece of software. You know, I'm pretending like it's this physical thing, but it was just a program, computer program that was mimicking the human brain, let's say. And we were trying to teach it how to do the multiplications table. So remember, you know, back in maybe second grade, something like that, you learn multiplication, you have the flashcards. They still do the flashcards? It's probably an app now, right? But when I was a kid, we had little construction paper in different colors, and I remember the red ones were the hard ones. So in any case, what we did is we fed the neural network the 1 through 5s table. And whenever it got an answer wrong, because initially it's just guessing, right? You're feeding something in, it's deciding what the answer is, and it's just spitting out random stuff. So chances are early on it's getting everything wrong. So then you're kind of doing this, slap it on the wrist, you go and update some things using some algorithm. One of them is called the back propagation algorithm. Not important for us, but we tweak the neural network a little bit until it starts getting the answers right. And we just keep feeding it those 1 through 5s flashcards hundreds of thousands of times until it gets all or most of them right. So now we've kind of balanced this neural network. It's been updated to now it can perfectly guess the 1 through 5s table, or close to perfectly guess the 1 through 5s table. But then the wow moment comes when you feed it the 6 through 10s table, data it's never seen before, and it gets them right. So I think I got like 97% of the 6 through 10s table right. So you kind of feel like, oh, I've like Frankenstein, right? You know, I've created a monster. I taught it how to do multiplication, but I didn't actually, right? I didn't articulate to it how to do multiplication. It's kind of this black box where I've fed it data, I've observed the output, and I've beat it up enough times in some interesting ways that it just started getting the answers right. That's sort of kind of intelligence, right? That's not a human being writing a piece of software that unambiguously solves a problem. Instead, that's a human being creating a piece of software that you can then manipulate to pretend to be us. And then through lots and lots and lots of iterations, it just starts getting answers right, and we don't necessarily know why. Kind of fascinating, right? But again, a human being, so from our perspective in here, we can only write programs that we can articulate the solution to. The first thing we have to do is we need to understand the problem we're trying to solve. Then we come up with our solution. We haven't started writing any code yet. We have to know, how am I going to solve this? Okay, if I want to cut up a stalk of celery, that's my goal. I'm going to need celery, and I'm going to need a knife, and probably a cutting board or something. You're going to have your little technique. You're going to decide, this is how I'm going to do it, right? Get all your tools laid out and stuff, and then you actually do it. That's when you actually hit the code and actually write the code that will cut up that celery. Okay? So kind of keep that in mind, that computer programming is hard. Most of you are going to struggle with it for a good point of the semester. Accept that right now. Just accept that it was going to be difficult for many of you, and that's okay. I'm not going to punish you. It's not like you're going to slide in with a D, put in the effort, you know, do the homework, do the self-assessment, work in groups, put in those reps, because I think I've mentioned that computer programming is kind of like a sport, where somebody can academically teach you how to hit a fastball, or academically teach you how to, you know, kick a soccer ball with some curve, or hit a 9-iron, whatever it is, you know, pick your sport. But until you've done it yourself a whole bunch of times, until you put those reps in, it's not going to click yet. Kind of make sense? All right, so do yourself a favor and put in the reps. Even though you might feel like, oh, this class is taking too much time, know that I'm not going to punish you for effort, but also understand that it's worth it, because ultimately you're training yourself on a superpower that allows you to do some pretty cool stuff. All right. All right, so we kind of already discussed this. What's an algorithm? Set of unambiguous instructions. That's that piece of, once you know the problem you want to solve and you come up with your solution to it, that's the algorithm for solving that problem. So if you take it away from computer programming, if you want to come up with an algorithm for making a lasagna, these are all your ingredients. You know, I'm going to make myself hungry by the end of class. These are all your ingredients. These are the steps you need to take. You know, some of them are mixing some stuff together. Some of them are preheating the oven, all these things. Every step that you need to take in order to ultimately bake a lasagna, right? That's an unambiguous set of instructions with a little bit of ambiguity for humans thrown in there. You know, when you do like the pinch of salt, stuff like that, where, you know, human beings like, it's, you know, was it got Emerald? Is he still on TV? You know, the whole BAM thing where he takes something and you're supposed to put a pinch of something. He goes, bam, 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 something like that, man. So anyways, a computer would want to know that we want exactly 2.7 grams of salt or something like that, where a pinch works for a human. But in any case, if you're making that lasagna off that recipe, we could think of a recipe as kind of being like an alternative name for algorithm. If you're making that lasagna off of that and you skip any of those steps, you risk that lasagna not turning out very well, right? You know, you forget the cheese, you forget to turn the oven on, all right? You know, things are going to go south real quick, all right? It's the, because with lasagna, you don't pre-cook the noodles, don't you? You just bake them. I think so. I don't know, that'd be a pretty crispy lasagna. I'd probably still eat it. Bakers can't be choosers, I suppose. All right, so that's this idea of an algorithm. You can think of it like a recipe, but it's very, very, very important that when we come up with an algorithm when we translate our algorithm into code, that algorithm needs to be unambiguous, because this guy's not going to read between the lines. The computer is going to want us to give it every little tiny detail. All right, so in the big scheme of things, I made a comment last class, and I'll say it again now, and you're going to hear me say it many, many, many times, is that computer programming is our skill set. That's what we're learning to do, is we're learning to be computer programmers in this class, in 250, in 300, that sequence of computer programming classes that we have. You're learning to be a computer programmer. In here, we happen to be using Python, but you're not learning Python. You're learning computer programming concepts that you'll see next semester quickly translate into Java. We spend like the first 2 days of class teaching you, here's the Java equivalent of this thing in Python. Okay, now you know Java. Go. Right? And then we just dive into some new stuff and start solving problems using Java. It's kind of like getting a new oven and a cooking set and stuff like that. Okay, you're working with some different tools, but they all pretty much do the same thing. All right, but when you look at a language, when you're, after you have computer programming as a skill set, you sit down to solve a problem. You might say, okay, well, what's the right tool for the job? Which language that I know is going to fit this solution the best? And then you might also then follow up by asking yourself a question, well, are there any technologies or languages out there that I haven't necessarily worked with, but are kind of predisposed to this kind of problem? If there are, maybe you choose to go ahead and say, well, I'm going to go ahead and just take a day or two and kind of get up to speed on that language and use that for solving this problem, because it's the right tool for the job. Okay, you can go out and trim the bushes outside with scissors, like my wife sometimes will do, or you can go and get the right kind of tools for doing that and accomplish it, but you have to kind of learn how the new tool works, right? Kind of the same thing. But once you get into some different languages, you'll kind of notice there's some classifications of languages. Like a certain language might fall into a certain category, and because of that category, you kind of know some truths about it. So we're going to look at them here in a few minutes. But like if I'm just looking at Python versus Java, for an example, these are the languages we work with in our first 2 programming classes, and here we'll be working with Python. So both of these languages are general purpose languages. They're designed to solve all kinds of problems that we can solve with a computer, all right? So they're equal in that regard. Python is what's called an interpreted language, where Java is a compiled language. Well, so right off the bat, that kind of, once you have some experience with those 2 different languages, you might start thinking, oh, this one's probably going to act a certain way. This other one might act a little bit differently under certain circumstances, just because of that nuance. Similarly, Python is a loosely typed language, where Java is a strongly typed language. And those things tend to go hand in hand with what I said just a second ago, where one's interpreted. Interpreted languages tend to be loosely typed. Compiled languages tend to be strongly typed. So again, as an experienced programmer, you might say, this is a loosely typed language. It's likely to behave this certain way under certain circumstances. Not a big deal. You just you're putting yourself into that mode for that kind of language. It's not that you can solve problems with this one and not with this one. You can still solve all the problems that you can solve with a general purpose programming language. You just have to, maybe when you're coming up with your solutions to problems, or you're deciding what's the right tool within the language to use, you might say, oh, well, this one's going to act a little funny and might not really be the best tool for this particular problem. So maybe I'll use a different approach with Python for this problem versus maybe Java. It's like, oh, this thing was just built for this problem, and you just solve it. So it just kind of gives a little nuance to how you might use those languages. We're not talking about, the black and white. We're talking about maybe there's a 9% little twist to your thought process with it, just a little bit. So like I said, the category of that language can tell us quite a bit about it. And once we've had experience with it, you'll kind of recognize that any of those strongly typed compile languages pretty much behave similarly. So C, C++, Java, C#, Swift, all those languages pretty much behave in the same category of ways, where our loosely typed languages like Python, JavaScript, PHP, these are all going to behave very similarly as well, and very similarly to each other, but they're going to have their own little compartmentalized nuances. All right, so this is something I just mentioned again, so I won't read the whole slide to you. The choosing the right programming language for the job. This kind of comes down to, you might start off with, what do I already know? And if it is, depending on how mission critical this problem you're trying to solve is, you might just kind of go with, well, I know Python, so I'm just going to, do this in Python real quick and move on with life. But if you're solving a larger project that has a lot of different, needs to hook into a lot of different technologies, you might take a step back and spend a little bit of time thinking about, okay, what are all the different things I'm going to have to interface with? Am I going to have to bring in Facebook? Am I going to have to bring in Google Maps and, different things like that? And you might say, okay, well, if I'm going to have to do all those things, is there a particular language or technology I might choose that just kind of makes that whole process go a little smoother? Something like that. All right. So here's the high level classification. And we're going to go into each of these after we talk about the CPU. But programming languages can either be high level, low level, or machine level. And we'll talk about that here in a few minutes. They can be compiled or interpreted. They can be loosely typed or strongly typed. They can be general purpose or domain specific. They can be object oriented, or they can be procedural. All right. So as a human being, computer programmer, a very, very, very high percentage of the languages we're going to be working with are going to be high-level languages. These are the languages that are most English-like. These are the languages that are least 0 and 1-like. Okay? Every now and then we have to operate in the middle here. There's low-level language, which we'll talk about that. Okay, we just mentioned this compiled versus interpreted. We'll talk about what that actually means, but that's another classification. Loosely typed versus strongly typed, another one. General purpose versus domain specific. So most of the languages you'll use in your career will be general purpose programming languages. You know, like here's a tool, you can use it to solve all kinds of problems. You can tell this computer to do all sorts of different things. But you also have some domain specific languages, like there might be a small programming language specifically for like working with a dishwasher. You know, the guy comes in, he reprograms it, he looks at the you know, the 3 or 4 different cycles the dishwasher has and realizes that, you know, oh, I need to, you know, because this machine's getting a little old, I need to increase the time that it's filling with water or something like that. Maybe it's the water is not filling as quickly or something like that, you know. But now you have a language. Usually these languages are actually based on other languages. So like a lot of the domain specific languages are based on like the old C programming language, but they are built to solve like 3 or 4 problems that are very specific to a task. All right, so those are things, once you get into some stuff in maybe in your career in a later class that deals with something called embedded systems, you might look at some domain specific languages that are kind of, you know, how do I make this, you know, you have a robot and the robot has, you know, 4 articulating arms. The programming language you're going to use is basically going to control the 4 articulating arms. That's what it does. You know, you don't necessarily get to go do a whole lot of other stuff. All right, and then object-oriented versus procedural, we'll talk about this. This is most of the languages you'll work with today are object-oriented languages. That doesn't mean you'll always work with them in an object-oriented way. And we'll talk about what that means as well. All right, so again, what's our job as a computer programmer? It's to tell this dude what to do. Tell a computer what to do. And I've already established today that computers are dumb, and we're going to try to articulate why that is here in a few minutes. All right, how many of you have heard of a CPU? Most of us, right? What is a CPU? You can start off with that, then tell me what it actually is. Okay, central processing unit. Okay, so think of it, brain of the computer, does the calculations, mission, I kind of put in here, kind of mission control. Computer only does things when the CPU makes it happen. You have other kind of complementing parts of the computer, but the CPU is kind of at the heart of it, right? Okay, so what actually is the CPU? Okay, so I like to think of the CPU as this collection of magic tricks. So we're going to start off doing a little fun exercise, and you know, and I haven't heard anything from the peanut gallery online very much, but everybody out there should be doing the same thing. So everybody raise your hand up. All right, now move your thumb like that. Oh, everybody can do that? It's not very impressive. What about this? Do you go around bragging to people that you can do this? Bragging to people you can do this? Oh, yeah. Oh, the one. Oh, I can do that. Look at that. And the Spock thing. Yeah. All right. So in any case, we don't go and brag to people we can do those little tiny stupid things, right? Every now and then you have that one person that could just do one weird thing that it's like, you know, something like that. But in general, you know, we all have like these same abilities, right? Now, how important is that move right there? Why? When do you use that? When you move your thumb back and forth like that, when do you use that move? Okay, yeah. When I grab this bottle of water here, I basically used my 2 moves we just looked at, right? I used that thumb thingy, and I used the finger thingy, you know, and we got this thing, you know, and then, oh, I'm gonna have to do some twist thingies here to get the thing open, okay? But we put together all those tiny little things that aren't that impressive in and of themselves, but we put them together in a sequence that ultimately allows us to accomplish tasks, right? Real tasks. So we all believe that that's a truth, right? We can even now step back and think about walking. right? If you start really trying to think about, how do you articulate walking, there's a lot of different things involved there, including, muscles, your brain firing, telling certain muscles to contract and extend and things like that. There's just a lot going on, but maybe each of those individual things aren't necessarily that impressive in and of themselves. Right? Your calf muscle contracts. Well, you could be at the gym and you could be flexing or something like that. And, maybe that's impressive, but in general, right, that's, nobody's like going to be clapping, because you contracted one muscle. But you start putting these things together in a sequence and real problems start being solved. Okay, the magic of movement, things like that, or locomotion, let's call it. So in any case, a CPU is kind of like that. It's, if we think of our thumb moving as like a magic trick, or the finger thingy as being like a magic trick, the CPU is this collection of magic tricks that in and of themselves, the individual magic tricks might not seem all that impressive. But once you start linking them together in an interesting order, real problems are solved. And if you think about the older CPUs, the older processors, they had a smaller collection of magic tricks than our newer processors, right? What's changed? Why are there more magic tricks in our newer processors than our older processors? What's changed with technology? Did we just decide that we needed newer things, or do you think that we probably wanted everything before, but we were limited? What was limiting us? Go ahead. Okay, sometimes we don't know we want something until it's missing. So you certainly have that. Let's say we knew we wanted it, but we couldn't put it on the processor. What are when you think about the manufacturing process, what drives price? Okay, well, so demand. Could be the material cost. Actually, maybe I asked the wrong question. I said, what drives demand? And one of the things is cost, right? So, you go out and you buy a new smartphone, you have this idea of the maximum amount you're willing to pay for it, right? Some people might just say, oh, I'll pay whatever I want. I want everything under the sun. Other people might say, okay, I'm willing to pay $500. I want whatever the best smartphone I can get for $500. Best being what's best for me. Maybe you really, let's say you take a lot of pictures, so you want the best camera. You don't necessarily care that it has, some extra thing that, takes your blood pressure or something like that. Different things are important to different people, right? Okay, so we kind of have that classification. We just think about it in terms of, this guy's basically a computer, right? He is a computer. The fact that it makes a phone call is also, I guess, somewhat interesting, but frankly, that's not even in my top 10 list of what my smartphone needs to be able to do. The phone call part is, in fact, I would almost maybe pay extra for it not to be able to do phone calls. Yeah, I want text, I want SMS, or Slack. Yeah, I want all those, like those kind of things. I don't want the phone calls. You don't know how long those are going to last. You can't ignore that. You can't be in the middle of a phone call and just pause them. It's rude. I haven't figured out Snapchat. That's beyond me. I don't know. All right. So, but in any case, what's been our limiting factor? Well, when you start thinking about a CPU, first of all, we have heat, right? We don't want the inside of our computers to get too hot, especially, you start getting third-degree burns from your laptop. We don't want that. And now the current move is what? Laptops don't have a lot of moving parts in them. So even now you have some laptops that don't even have fans. Everything's done with thermal distribution, trying to get the heat out from the central area. So the thing gets pretty warm, but they try to match up the right level powered processor with the things this laptop was designed to do. And it might not be the highest performance thing, but it might be high enough performance to solve the problems it was meant to solve. So now with that in mind, with that in mind, the another thing is you've maybe heard when, the latest, greatest processor comes out, they talk about the nanometer technology that they're using. This is 16 nanometer or 14 nanometer or 10 nanometer. And what that has to do is when they print the circuit boards, you know, whatever technology we have to actually make the processors, they're able to get the little wires closer and closer and closer together without them conflicting with each other. And if you look at a computer processor today, you compare it to a computer processor 25 years ago, they're roughly the same physical size. But today we have the technology to fit more stuff in that same physical space. And then we have to think about, well, how much more heat will this you know, generate, and how do we distribute, you know, how do we take care of the heat? Well, you got these gaming PCs, everything's liquid cooled now, right? So yeah, we can let it get as hot as we want. We're just going to dunk the entire machine in liquid ether. It'll be fine. You know, so we have, you know, like these overkill solutions to some of those things now, but in general, these are problems that have to be overcome. We can't just have a CPU that, you know, is the size of a building, that has every magic trick that we might ever want in it, you know, and we don't care about heat. We just put a lot of air conditioning units on there. We just don't care about electricity. We could make that. We could technically create that monster, you know, but you're not going to have people, you know, buying the latest MacBook Pro or the latest Dell laptop or HP, whatever, that, you know, have the building CPU in it. You know, it's not a practical solution. So we've had to make choices. So one of the things that you think about the Intel, the CPU makers like Intel do, is they have to figure out, if I have 500 magic tricks that I could put on the CPU, what are the 500 most important magic tricks? And I say that because, you know, we go back to our example here when, you know, we saw that for the grab move, when I want to grab something like the water bottle, that's putting together 2 or 3 magic tricks in a row. Now I can have those 2 or 3 individual magic tricks on the CPU, you know, and I probably should, because I might use those for other things. But do you think that you grab things very often? Is that something that we do as a human being very commonly? So it's very common that we put together those 3 or 4 magic tricks. So maybe it would be worthwhile throwing kind of an extra magic trick in there that's kind of like the, you know, the super grab move, right? It just puts all those things together automatically without me having to, you know, have a sequence of events. And maybe that's worth using some of the CPU real estate for, is to have those kind of things that get used often. Which then kind of goes into the selling process for some CPUs, you know, and the current trend of CPUs is, you know, now they have a Intel Core i9 processor, but let's just look at the Intel Core i7. We're currently on the, they just came out with the 9th generation Core i7 processor. So, and each time they come out with the next generation from the Core i7, they'll say something like up to 30% faster than the last generation. Well, but the last generation was 30% faster than the one before that, but they always say up to a certain amount faster. What does that ultimately mean? The processor itself is not faster. If you take take the little thumb wiggly thing, okay, that's not going to be any faster on the 9th generation versus the 3rd generation. What they've done is, as they've been able to squeeze more things onto that chip, they might look at a particular technology that has become commonplace. Maybe encryption technology, since we're doing a lot of stuff with security and things like that. They might throw a magic trick on there that takes 2 or 3 of the magic tricks from the previous generation and optimizes that. And that particular magic trick, let's say, is 30% faster than what you used to be able to do on the previous version of the processor. That's where that up to 30% faster comes from. Now, if you're going to do that thing very often, it might be worth it to you, right? Having that new processor at, you know, twice the price or whatever it is, might be worth it to have that one extra magic trick that does the super grab move, you know, something like that. But more times than not, those things that make the processor up to 30% faster probably don't apply to you. And if they don't apply to you, there's really no reason for you to upgrade your computer with that processor. So something to kind of keep in mind when they say something is faster, it probably is, but it's probably situationally faster when you're dealing with the current trend of things. Because if you go back the last like 15 years, our processes are typically measured in so many gigahertz, right? You have a 2.4 gigahertz processor, something like that. Well, 15 years ago, you could get a 2.4 gigahertz processor, and you can get a 2.4 gigahertz processor today. Now, those aren't necessarily completely equivalent because you do have different architecture behind that, a different set of magic tricks, maybe different power consumption. Maybe 2.4 gigahertz processors today use less electricity than 2.4 gigahertz processors back then. But in the big scheme of things, we really haven't noticed this drastic increase in the performance of our processors, right? Not like it was in the earlier days of computing. Well, why is that? What's our limitation? Well, it's heat. It's the nature of silicon, which is the current stuff we're using to build our processors. So what are we looking at? So now what do? Since we can't make an individual processor any faster, what have they started doing? When you get a new computer, it's not just, oh, I have a Core i7 processor. Now it's how many cores? Before, it used to be cool when you had a dual core processor. You can't even buy a dual core processor now. They're all quad core, 6-core, octa-core. Intel has an experimental processor that has like 128 cores. Not quite the size of a building, but it's probably the size of a toaster or something. They just keep stuffing more and more cores into it, right? And then with the magic trick thing, they kind of shove things like called logical cores. Put logical cores in there. So one of the earlier technologies that Intel had, and they keep coming up with kind of new names for it, and new turbo this, turbo that, is something called hyper-threading. That just sounds fast, right? Hyper-threading. So hyper-threading will make your 2-core processor act kind of like a 4-core processor, with an emphasis on the kinda. Well, just put it in quotes and we'll move on with life. We won't talk about that, right? It does. It uses, when you take the computer architecture class, we talk about some techniques you can use to maybe get the next magic trick loaded into the CPU a little bit quicker through something called pipelining. And so hyper-threading kind of takes advantage of that. Then you're also at the mercy of the operating system. An old funny thing from many years ago, back before Apple was cool, but they wanted to be cool. So Apple, this was when they were not using Intel processors yet. They were still using PowerPC processors, and they had the PowerPC G3 processor. And then they came out with the G4 processor. Great naming convention, right? So the G4 processor had this technology in it called AltiVec. That was before, AltiVec just sounds mysterious, but I think hyper-threading sounds more powerful, right? But AltiVec was something that allowed them to do, certain kinds of computations much quicker. Fine. This was before, today we think about processors being multiple core processors. That's a single physical processor with multiple CPU, a single physical piece of equipment with multiple processors on it. So rather than having this guy become faster, they say, well, we're just going to have more of this guy, but in the same space. Well, back then, they weren't doing that yet. They were having machines that had dual processors, where you'd have 2 physical processors inside the computer. So Apple, this was back when I think the OS at the time was OS 8 on the Mac, way before OS X. We're in like in the 11th or 12th rendition of OS X. But in any case, so Apple comes out with the dual G4 computers for the same price as the one with just a single processor. 2 heads is better than 1. They had these commercials that talked about like it was the first supercomputer you could have on your desk, and they had tanks and stuff like that in this commercial. But what was hilarious about this is you had this hardware you just bought that had 2 physical processors in it, right? The operating system, OS 8, and also OS 9, did not support more than one processor. So this machine was shipping with an operating system that did not support the second processor. Yeah, kind of funny. At the time, though, you did have Photoshop, which did take advantage of the second processor. So you had a couple of specific pieces of software that would leverage that second processor, but that's something only some people were going to benefit from. So again, this is almost like consumer control, right? A lot of times what we're told isn't necessarily in line with reality. So something to keep in mind when you hear like, oh, a CPU is 30% faster or whatever. It might be, and it might be something that's important to what you do in your daily life. But at the end of the day, from our perspective, we want to think of the CPU as being this collection of magic tricks that, you know, ultimately, when the computer does something, it does it as a result of us saying, do magic trick 1, then magic trick 7, then magic trick 14, and something's been accomplished. That's the whole grabbing the bottle thing where I perform a couple of the different magic tricks that the human body can do. Make some sense? And that's what the CPU is. That's how we should kind of think about that CPU. All right, so in general, we like power tools, right? We already decided we don't want to be talking to that CPU. I think last time, didn't I show a Hello World program in Linux, or did I not show that? Are you lying? Maybe? Did I show this last time? Okay, well, we'll come back to it here in a second then. So we certainly don't want to have, I mean, we can all agree we don't want to have the 2-button keyboard where we're just talking to the CPU, you know, just pounding out zeros and ones. Certainly don't want to do that. Now, we could talk to our computer, you know, like if you were telling somebody how to grab a bottle of water, right? A human being would just say, well, you just grab it, right? that's what you do, just grab it. You know, and you might show them the move in slow-mo as you grab the bottle of water. But you probably wouldn't say, okay, you bend your thumb like this, and you probably want to maybe lead with the index finger. You know, I like to go with the index and the ring finger. It helps to, give stability. We don't go into that level of detail, right? So, so in general, we could get more granular than that, but even then, that's not in our comfort zone. We really want to just say, oh, just grab it. We like power tools that allow us to accomplish our tasks. So we want to work with, ultimately the job of a programming language is to tell this computer what to do. We want to work with a tool that allows us to operate on our terms, but that ultimately gets the stuff down to the level of telling this guy what to do on his terms. Okay, and that's a pretty big chasm we have to cover. Let me just see where we're going with this. All right, I'm going to talk about this slide quickly first, and I'll go back and talk about some of those other things. So we have this idea of high level versus low level versus machine level code. I'm going to give us some definition to the binary stuff, the zeros and ones here in a minute. But when we talk about machine level code, we're talking about zeros and ones. Low level languages, this is where we kind of, this leverages this idea of what we just talked about with CPUs, is a low level language has a one-to-one relationship with the CPU. Every line of code we write in a low level language translates into exactly one of those magic tricks on the CPU. Okay? And to show you an example of that, this is the Hello World program in Intel-based assembly for the Linux operating system. Because when you ultimately compile code down, this is actually still using a power tool because it's using the operating system itself. But I'll kind of walk through this and give you an idea of how this code is actually working, so you kind of get this idea of how do operating systems actually run programs. All right, so forget about this top stuff and even the bottom fluff. Just see that we have, down here we have a couple of variables. We have hello world, and then we have the length of hello world. That's what these two things are down here. Okay, so I'm just up here and the program begins where it says start. All right. So one of the magic tricks that an Intel-based CPU knows how to do is knows how to move. Okay, it's moving something from one place to another place, typically in memory. All right, so these first four things that I'm doing here are just moving stuff, kind of like moving chess pieces around. So I'm moving the length of the message. Ultimately, I'm trying to write hello world to the screen here. So I'm moving the length of my message into this memory location. EDX is something called a hardware register. It's a piece of memory that lives right on the CPU. Okay, not that important, just it's a memory place. All right, so I'm moving the length into this memory place. I'm moving the actual message, hello world, into this memory place. I'm randomly moving the number 1 into this memory place, and I'm randomly moving the number 4 into this memory place. So I've just put 4 things in 4 different buckets. All right, but now the buckets that I put them into here were very, very, very important. The fact that they were put in very specific buckets is what makes the computer ultimately work. Then I'm interrupting the CPU because I'm saying, operating system, in this case Linux, I need you to take over. Go and do some of this stuff for me. Do the heavy lifting for me so that I don't have to write 6,000 magic tricks in a row here to accomplish something, because somebody else has already written those 6,000 magic tricks in a row. You know, the operating system. The operating system sits between the human being and the computer and makes our lives easier. It's one of the things that, you know, it's kind of a go-to move of an operating system is to put stuff on the screen so we can see it. So somebody already wrote that. So when we interrupt the program, interrupt the CPU and say, okay, turn it over to the operating system, what does the operating system do? It immediately looks at EAX, this memory location, and says, which magic trick, and in this case, magic trick is which system call on the operating system are you wanting me to perform? This number 4 happens to correspond with the syswrite system call. This is the system call that knows how to write stuff to the screen. It knows how to write stuff, okay? And because we're calling the syswrite system call, that then lets Linux know that, oh, I need 3 different inputs for that to work. I need to know what I'm writing, how long it is, and where am I writing it to. I need 3 things to do my job. Just so happens that we gave him 3 things. So he's going to go and look in EBX and finds this number 1, and 1 relates to standard output. That's the where am I going to write this? Standard output's the monitor. All right. Then it's going to say, okay, well, what am I writing? I'm writing this message. Because it looks in ECX and finds out the what am I writing. It looks in EDX and finds out how long is it. We'll talk about that when we get into lists and arrays in here, but you know, knowing where this guy is effectively, where does the message start? And this is how long do I have to keep going until I run out of the message and start getting into random memory stuff. Okay, so this gives us our 3 pieces of information that this guy needs to solve its problem. Go ahead.
I was just wondering, how does it know which way to like parse through it? Is it actually going back up like that?
It doesn't matter. I mean, when this program runs, it just performs these 4 steps. So at the end of those 4 steps, these 4 places in memory have this data. It doesn't matter how Linux, whether Linux reads, you know, this one first or this one first or this one first, it will check this one first. It's going to say, what do you want me to do? And based on what do you want me to do, I need this many inputs, and this is where I'll find them.
The reason I asked is because I was curious if you like wrote those in a different sequence, would that screw it up?
If you wrote these in a different sequence, and wouldn't, because you're not actually asking the operating system to take over till here. You couldn't, I mean, the exception to that would be if I moved this line to the top. Then I'm saying, OS, take over. I haven't really given you anything yet, but, you know, just kind of dance or something, you know, whatever it is you do. So you definitely need to stage the data first, but the order in which you staged it here is unimportant. All right, so, but ultimately this is how low-level code interfaces with the CPU. There is a little step between this where this line will get turned into a bunch of zeros and ones. This move command might be command 0001011 or something like that. You know, it translates into some number. But that's just a lookup thing. You know, that it has magic trick 1, magic trick 2, magic trick 3, and we'll talk about binary and decimal numbers here in a second, more next class. But you know, the idea is that this is basically one magic trick at a time. I mentioned a slide ago, or the current slide, that you know, a low-level language has a one-to-one relationship with the CPU. Every one of these lines is one magic trick. Wiggle your thumb, do the finger thingy, you know, that type of thing. That's what each of those lines mean. All right, and then when we turn it over to the operating system here, which is a power tool, that's something we didn't have in the early days of computers. Early days of computers, you go and look at like a EDVAC and UNIVAC, you know, that used vacuum tubes. You know, you didn't have an operating system that did the work for you. You had to physically go up and turn on little light bulb looking things to load these values. So it was, you know, a very different kind of situation. But now we have these powerful operating systems that even this that looks really complicated is far less complicated than it used to be, because there's a whole lot of magic in that program right there. That's already part of the operating system that's doing a lot of this heavy lifting for us so that we don't have to. We're taking advantage of the fact that Linux already knows how to write stuff to the screen. Make sense? All right, so to write it to the screen, we stage 4 values, then we tell the operating system to take over. The operating system says, you want me to write something? Okay, where am I writing it? What am I writing, and how long is it? Does its thing. Then in Linux, a lot of system calls have like return codes. So when the program finishes, it'll give you a 0 if everything worked fine, or something other than 0 if something went wrong. Kind of like if you think on web pages, sometimes you get like, you know, error 505, stuff like that. Each one of those numbers means like a different problem happened. Otherwise, the page just loads. So it's kind of like that. This is relatively unimportant in terms of the functionality of this program. It's just saying that, you know, when you make a system call, it returns a 0 when it worked. All right, so we're loading a 0 into EBX, and then we're overwriting what we used to have in EAX, which was a 4. Remember, this is the first place the operating system looked, was inside of this memory location. And it used to find a 4 in there, which corresponded to syswrite. But now it's going to find a 1 in there. So we interrupt, operating system goes again, sees that, oh, there's a 1 in here. No problem. What is 1? That corresponds to the exit system call. Program's done. Spit out 0, everything went fine. Hello world's been on the screen. It actually got put on the screen from that sequence of code. And now this program has completed based on that sequence of code. All right, kind of makes sense how a low-level language works in conjunction with our operating system. Now, when you look at that, we just walked through this. This was human enough that you could tolerate us going through, you know, 8 lines of code. How many of you would want to write this yourself very often? Doesn't seem that fun. It might seem cool for like a day. Like, you know, look, this is my life. You know, I talk to CPUs. You know, I put pants on one leg at a time like anybody else, but then I speak binary. So it's a thing. But the coolness factor wears off pretty quickly, and we start realizing, you know what, I'm still human. This really isn't my cup of tea. You know, we're going to be very error prone, right? You know, think about it. You know, you're trying to teach somebody how to grab a bottle of water, and you forget to tell them about the thumb thing. Yeah. I had to squeeze pretty hard. I can make it work. But if you forget to tell them about the thumb thing, you might run into problems. Well, that's just giving them a couple little instructions. You imagine, I'm just making up a number, but I bet the number of magic tricks that are part of the syswrite thing is many, many hundred. Let's call it 500 magic tricks are being called for the syswrite to work. That's completely hidden from us. We don't even see it. We're calling it like it's a single magic trick, but it's actually just another computer program that we're turning this over to. That's already part of the operating system. So the reality is, if we had to write all this ourselves, I mean, this is bad enough, these 8 lines. But what if we had to write 1,000 lines or even 100 lines? We're going to be pretty error prone if we are operating at that level of detail, right? You know, because I mean, we can sit there and manipulate it, do trial and error until we finally just get it right. And we have, okay, we have 230 lines and these work, you know, and I spent hours and days debugging. I forgot one little magic trick, something like that, but now it works. And now whenever you need to do that, you can just call upon that. Well, wouldn't you rather have that process be automated where like, okay, the working solution for something as trivial as putting hello world on the screen has already been created for us. And all we need to do is say, print hello world. And the magic behind the scenes just kind of happens because somebody, a human being, did write it at some point. And it was complex. And they went through lots of trial and error to make sure they got all the granular stuff there. But now we can take advantage of it. Make sense? All right, so, you know, we can look at this and we can appreciate what's happening under the hood. We can say, you know, in small quantities, I could even tolerate it. But maybe I don't want to very often. We like power tools. So coming back to this, that's where we get to our high-level languages, which will represent most of the languages as computer programmers will deal with. Okay, these have a one-to-many relationship with the CPU. So in Python, I might just say print hello world. One line of code that sounds pretty English-like. And that will magically, one way or another, we'll just say for now, turn into this, which then one way or another for now turns into zeros and ones, which then runs on the CPU. Well, we didn't have much to do with this part. We didn't have anything to do with the 0 and 1 part, and ultimately the operating system is what made it show up on the screen. So all we had to do as a programmer is write, print, hello world. That's more our speed, right? But then that also now lets us solve more complex problems like your video games, all the big explosions and things like that, because most of the programs we write, like none of us are that impressed with this idea of writing a program that puts hello world on the screen. Right? That's not earth-shattering. You know, you're gonna have a rough job interview if you say that's the extent of your skills. Okay. Well, you know, I can also print other words, but hello world's kind of like it was my go-to. You know, something like that. But you know, the reality is that because we have this power tool, we can now solve more complex problems because we're not having to get into the nitty-gritty of these little things. Instead, we can focus on our algorithms, the recipe to solve our problems, and focus on things that are at a much higher level, still cryptic, right? You know, whenever you think about coding, programming, coding, whatever, you know, you think of that as being kind of cryptic, kind of like almost looking at another language, you know, it's all Greek to me, that those types of things. But, you know, when you are a programmer, and you're used to seeing those different things, you'd much rather be reading high-level code than low-level code and way more than binary, machine-level code. All right, so zeros and ones. This is what we just looked at, those individual granular instructions. But this is what we're gonna actually be operating with Python. So for instance, if I just bounce over here to Python, we wrote this last time, print hello world, hit play, ultimately puts hello world out on the screen. But behind the scenes there, a whole bunch of stuff was happening. Make sense? All right, now, as humans, we can handle that, right? We imagine it's gonna get a little more complex than that, but if every line kind of sort of looks like that, we can, that's in our wheelhouse with some practice. Okay. What time are we at? 11:20? Okay. All right, so actually, just for time, let's go on to the compiled versus interpreted piece here. So what a compiled language does. So we just talked about this idea of high level versus low level code. A compiler, which compiled languages use, will take our high-level code like this and turn it into low-level code like this before we run the program. So it does that translation ahead of time so that at the end of the day, what we have is we have an executable. You know, if you're on a Windows machine, it's a .exe file. You know, that's our program that is ready to run. And what that is that has been a file that's already been compiled, already been linked with any external libraries it needs from the OS, and already turned into the zeros and ones, packaged up into an executable format that you can just double click on and it runs. All right, so that all happens before you ever run it. Okay, so a compiler translates our high-level code that we write into low-level code before we even run it. Make sense? Whereas an interpreter, interpreted programs, these guys do the translation during runtime. So when I hit play here, so Python happens to be an interpreted language. When I hit play here, it's actually starting to run my program, and it's taking this high-level code and translating that into low-level code. It actually never goes to low-level code because what it actually is doing is the interpreter in Python is written in a compiled language like probably C or C++, which is then translating that into the equivalent instructions for the CPU. But the difference is an interpreter does this during runtime. A compiler does that translation prior to runtime. Okay, so if you want to think about a real-world example of this, if the president's giving a speech and they release the speech an hour ahead of time, let's say it's the president of France or something like that. So the speech is in another language, okay? And the news station has an hour to convert the French into English or whatever the news station's language is. You know, that's probably going to represent a more accurate translation of it because they had time to get it right, as opposed to if they're, you know, on live TV and well, at least it's going to be faster when they read it, right? So when they actually deliver the German version of that speech, you know, they can just read off the already translated thing. It'll go fast. Whereas if we were dealing with a real-time speech with an interpreter, you know, the French president's giving the speech and the interpreter's converting it to German in real time. At the very least, that there's going to be a lag, you know, a little bit of slowness there, right? Now, in general, when we think about computing, we might say, well, faster is better than slower, right? Most of us would say that, even though most of our newer languages that come out these days are interpreted languages like Python. Why do you think that is? Why is slower okay? What does slow mean when it comes to computing? None of us like when our computer feels sluggish, do we? But do you care if your computer feels fast? If my computer and your computer feel like they're the same speed, but my computer has way more horsepower, does that bother you? Or are you just laughing your way to the bank because you spent a quarter of what I spent on mine? As long as it's fast enough, you don't care. Speed is relative to what a human being will recognize. That make sense? So the short version of this is computers are really, really, really fast. And because computers are really, really, really fast, interpreted languages are fine for most programs. You are not going to see the latest Call of Duty being written in Python. Okay, so those, you know, games and things like that really are reliant on speed. And because of that, they typically are written in compiled languages, which also happen to be strongly typed languages, which we'll talk about later. But that's where speed really matters there. Operating system speed really matters. But call it 99% of the programs we write, who cares? We got an octa-core processor in our computer running at 3 gigahertz. It's fine. We got enough power. It'll fake it. Make sense? All right, questions, comments, concerns, bribes. Remember, Bible homework's due by midnight on Sunday. Also, everybody should be working on getting Raspbian installed on their VirtualBox. I'm guessing you will maybe need that for next Thursday or maybe weekend homework over the weekend. Okay, so that's your assignment for right now, is be working on watching videos, talking to your classmates, get a version of Linux installed on some machine so that you can do your homework using Linux. Make sense? All right, I'll see everybody on Tuesday. And I didn't hear anybody from our audience. Everybody in the audience could hear me, right?
Yeah.
Okay, just no questions today?
I have a question.
All right, go ahead.
You said that you put a link on the Slack.
Correct.
Oh,
It's in the CSC200 channel.
I'm not even showing that. Mine just says general.
I think if you go to, what is it? There's like an ad channel thing. See, I see them all on mine. Anybody know when you went to get into the 200 channel, Ben?
I'm trying to remember what I did, but I think I clicked browse Slack.
Okay, like somebody's saying like they click like browse channels or browse. There's you know, a button over there somewhere that will let you
Okay.
like, you know, join the different channels.
No, I went to cuwcs.slack.com and that brought me directly to the computer science Slack.
Correct, but he's saying he's not seeing 200 over here on the side. He only sees general.
Okay, wait. I think I just found it.
Okay.
And then yeah. All right.
And then
Thank you.
do you see the couple of things I posted in there?
Yeah.
Okay. Or worst case here, it's on the video now. So,
All right.
all right.
Thanks.
Yeah. And again, for next time, if you're in the online audience, feel free to just scream out and interrupt me. I want to make sure you guys feel like you're part of the class. You're not going to offend me, I promise. Yeah, try to jump scare me. That's right. Whoa! Do one of the air horns. All right, well, I'm going to end Zoom so it can start converting the video, and then I'll get it uploaded here in the next 20 minutes or so.